Okay, grade 9s. Now we're moving on to 8.3, which is the properties of angles in a circle. In this lesson, we're going to give you a review of what we've done previously, and then we're going to add in the inscribed angles and central angles and some one more property on tangent theory. And then we're going to put it all together and solve problems. So let's get started. So first off, before we begin, let's start with the perpendicular chord theory. Now, this theory states that if this here angle here is y, then this angle, this length here, and this length here will be equal. Now, watch what happens as I start moving things around here. See how, look at the lengths of CE and ED. See how they're always the same? And look at the angle here between the perpendicular bisector, which goes through the middle of CD. It always stays at 90 degrees, no matter where I move this. It also doesn't matter what size the circle is. So this is the theory. It states basically that if this is a perpendicular bisector, that CE and ED will be equal. And of course, being a perpendicular bisector, that y has to be 90 degrees. Let's take a look at the tangent properties now. Okay, now this should be familiar to you. D and E are tangent points, right? And this is a point outside the circle. And you'll notice that this is 90 and this is 90. And as I move this around, you'll notice that they stay 90, don't they? Doesn't matter where the outside point is. If those are tangent points, they stay at 90 degrees. The other thing you should also remember is that DC and EC are always the same. We use this when we're doing the plate questions. Remember that, or the pendulum questions. So, or even the ones we had the plane above the horizon, sorry, above the Earth, looking to try to find the horizon distance. All right. So these are equal. These are both 90 degrees. Now the third one is new. In this one, I want you to take a look at angle A, or sorry, I guess it's alpha, but it's that angle F there, right? It's 43 degrees. Now look, this is a tangent point here, right there. And look what happens from when you have the triangle in there. Do you see that? This angle here, from this line to the tangent line, and this angle here are always equal. Look at that. Doesn't matter how big the triangle is. You notice how they always work out to be equal. So we're going to use this a little bit later, but if you see a tangent line and a tangent point, and you're given the angle on the outside of the triangle to the tangent line, that angle will always be equal to the angle that's the farthest away from it. Okay, so this is new stuff. We're talking about major and minor arcs. Now, an arc is a section of the circumference of a circle. So it goes from this point A around to point B. That's one arc. The other arc goes from A and it goes around the different direction, the larger one. Now, because this is the longest distance, it's referred to as the major arc. This one here is the smaller one. So that's called the minor arc. So when you tell somebody about arc AB, you have to specify whether you're talking about the major arc or the minor arc. These are called central angles and inscribed angles, and they have a relationship between them. A central angle is in the center of your circle. It goes, there's your center O, and it's the angle between A to O to B. That's called your central angle. And it's called the central angle because it's in the center. Now, when you draw an angle from the circle down to the same points, A and B, we call this an inscribed angle. So central angle is in the middle, and inscribed angle is on the outside. Now, the word which is going to be used a lot is called subtended. Now, subtended means that they share or they talk about the same arc. So, for example, central angle AB is subtended by inscribed angle ACB. It means that they're both talking about the minor arc AB. One is measured from the center, and one is measured from the outside of from the circle line. Now, I got an exercise for you. I want you to get your compass, your straight edge, and your protractor. I want you to draw a circle with the center O. Make sure you mark the center because you're going to be drawing other things in there. Choose 2 points on the circle, and I want you to label them A and B to form a minor arc. On the major arc, I want you to place point C, and I want you to draw AOB. Okay, put the central angle in and the inscribed angle. So take and pause the recording, and I want you to draw that this project here. Okay, you should have got something that looks like this. There's AB. There's my minor arc AB, and there's my central AOB. That's my central angle. I have an inscribed angle ACB. Now that point C could have been anywhere on here, but the ends will always end at AB. Now, when you measure this, that's what I want you to do next. I want you to pause the recording, and I want you to measure this angle. And then I want you to measure this angle here with your protractor. So pause the recording and do that right now. All right. Well, your central angle is not going to be the same as mine because your points A and B are at different locations. But my central angle was 98 degrees. My inscribed angle was 49 degrees. Now, what do you notice about that? 49 versus 98. Well, you should have noticed that this angle here is half of this angle here. Inscribed angles are half of central angles when they subtend the same arc. Now that's critical. If they don't subtend the same arc, there's no relationship between them, right? So you measure ACB and AOB, and you can see what I got right here. You all have different numbers there. Now add another point to your diagram. So go back to what we had here. I want you to add another point, and I want that point to be labeled D, and I want it to subtend minor arc AB. All right. So add another point on the major arc, label it D, and have it join point A and B. So I want you to inscribe point, another angle, to fit the same arc AB. Now I want you to measure it. So pause the recording and do that. Okay, you should have measured, and it should be the same as your other inscribed arc. So what we're talking about here is that if this is what mine looks like, you'll notice my point D is 49. My inscribed angle at C is 49. Now 49 times 2 is 98. So this inscribed angle and this inscribed angle are half of this central angle. Now you could look at it from the reverse and say that this central angle is double the inscribed angles. So 49 times 2 gives you 98. 49 times 2 gives you 98. So let's take a look at what this looks like when you start drawing it. So you can see here I've done exactly what I had there before. I've got my AB arc, I've got my C and D, and I've got my center. Now look what happens as I move this one here around. Do you notice something? It doesn't change, does it? So it doesn't matter where you put C, as long as it subtends the same arc, minor arc AB, it's always going to be the same angle. Look at this one here when I move it. They don't change. Now if I were to move B, look what happens now. All right, 121. Divided by 2, 60.5, 60.5. And again, as I move it, it doesn't change. So as long as inscribed arcs, multiple inscribed arcs, subtend the same minor arc as the central, they will always be equal. So anything out here is always going to be half of what's here. All right. I want you to add an inscribed point, E, which subtends the central angle onto your drawing. All right. Now you should have found that AEB minus 49 degrees. So this is what it looks like. We have the same thing all over. All right. Inscribed, inscribed, inscribed. Notice they're all 49s. Now, here is the GeoGebra file. You can take a look at what's happening here. Okay, look at this. I want to make this so it works out to be nice and beautiful. See if I can get that to be 100. I guess I can't. Oh well, 115. But look what happens here. E, C, D are all equal. B, no matter what I do, look at angles, the inscribed angles. No matter where this is, they always are the same. Same if I move point A. Right? So again, this shows you all inscribed angles are half of their subtended central angle. So, conclusions. This is what we conclude here. First off, the inscribed angles on a major arc of a circle are half the central angles. So that means that this inscribed angle is half of the central angle. And it's true, 49 is half of 98. Number two, all inscribed angles on a major arc are equal. As long as they subtend the same minor arc, D, C, and E, these three are always equal. Now, all inscribed angles on an arc formed by the endpoints where we have a diameter is equal to 90 degrees. Now, this is new, so I'm going to go back to the algebra program we had just a second ago. And we're going to see if we can make a diameter. All right, look what happens as I start making this closer to 180 degrees. Don't know if I can get it there. Right? Not quite there yet, right? But you notice that this is if this was 180 degrees, that would be 90, and that would be 90. Now this is critical because there's going to be some problems that you have to solve which become very, very difficult if you don't know this property. The moment you go across a diameter, these make 90-degree angles. And the moment you have 90-degree angles, guess what you can use? Pythagoras' theorem. So that's very important. So we've got inscribed angles, we've got central angles, and we have our conclusions now. Inscribed angles are always the same if they subtend the same central angle. All inscribed angles on the major arc, if they subtend the central angle, are equal. And if you go across a diameter, it's equal to 90 degrees. We're going to go on now to example 1 using inscribed and central angles. Now it says here that point O is the center, and I want you to find the angle at X and Y. Now if you look at X and Y, there's no relationship between them because there's nothing you can do. You can't get X or Y from each other. So you have to look at what else is included. Now look at point C over here. See point C? Point C is subtending the same minor arc AB as X is. And we know that anything that subtends the same minor arc, their angles are equal. So that means if this is 50 degrees, X has to be 50 degrees also. Now, let's go to angle Y. Now we know that this is 50. We know that's 50. We know that Y is the central angle to AB. Since this is 50, we know that Y has to be double it because that's the relationship between an inscribed angle and its central angle when they subtend the same arc. So if this is 50, this has to be double 50, which is 100 degrees. Okay, so copy all that down and pause the recording and copy that down. Okay, moving on. Here's our next example. This is again testing whether you know the relationship between inscribed angles and central angle. You'll notice I've got A, B, and C here. These are all inscribed angles, and they're subtending the minor arc AD, sorry. And you'll notice that the angle at AD is 166 degrees. So this is asking you, do you know the relationship between its central angle and its inscribed angles when they subtend the same arc? And you should know that if this is 166, A B, and C all are half of 166. So that gives them 83. Since angle A is inscribed angle from AD, it's half of the central angle, and therefore it's 83 degrees. Now, you can use the same rationale for B. This inscribes the same angle, so this is going to be half of 166, and this is going to be half of 166. Or you can go the other route. Since all inscribed angles on the same arc are equal, if that's 83, that's 83, and that's 83. So both ways could be thought of. Okay, so pause the recording and copy down your notes. Right. Now, applying the property of an angle inscribed in a semicircle. All right, here we go. Now, a rectangle is drawn inside a circle, which has a radius of 30 millimeters. The length of the rectangle from here to here is 45 millimeters. What they want to know is, what is the width? Now be careful, this is not a square. All right, it's not a square, so you can't just say, oh, it looks like 45 and 45. It's a rectangle. So we have to answer this. Now, when you look at this one here, it's kind of, if you notice something about the circle and a rectangle, when you go across a rectangle, you always go through the middle. So let's add that line in here and see what we've got. What's that? Now, if you look at this, that's 30. That means that this over here is also 30. Now, 30 and 30 means that the distance from here to here is 60 millimeters. And the distance from here to here is 45. Now, how do we solve this? Well, I told you before that if an arc, let's just call this, I don't know, call it G. If point G subtends the diameter, we know that G is a 90-degree angle. Now, the moment you know that G is a 90-degree angle, now we know we can take this and this and this, and we can work with it. Now over here, this is our width that we're trying to find. So I now have my hypotenuse, and I have one of my other sides, A or B, and I need to find the other one. So this is the description that I did. Since the rectangle has a 90-degree angles, we can use the Pythagorean theory to solve this question. The distance across the rectangle is a diameter, so it is 60 millimeters. This gives us the right angle triangle that we can use right here. Now to solve this, I've drawn it out so you can get a better look at it. Right? We also know that this is 30. So 30 and 30 means that our big length over here is 60. Now, how do I solve that? Well, pulling up my Pythagoras theorem, since I'm trying to find A, I'm going to call width here A. I'm going to call this B. And of course, my diameter, I'm going to call that C. Oh, I guess I used L in the other one. Okay, we'll use capital L so that it matches up. So the length here of the hypotenuse is 60. A is the width, and B is the other side. This is a right angle triangle, so it's easy to solve. So here we go. A squared is equal to L squared, or length squared, take away B squared. And my length is the 230s, so that means that I've got 60 there. Now 60 squared is 3,600, and 45 squared is 2,025. Subtract them, and you get 1,575. Now take and square root that, and you get 39.7 millimeters. So that means the width of our rectangle is 39.7 millimeters. Now, up until, I did this one for you because I wanted you to take a look at this question and see how you had to add pieces to it and use the knowledge of your theorems and all your properties in order to get your right angle triangle to solve it. Here we go. Now it says a square with a side length of 100 millimeters is inscribed in the circle. What is the radius of the circle to the nearest 1/100th of a millimeter? All right, I want you to pause the recording. I want you to add what you think you have to add here, and I want you to solve this. All right, well, the first thing you should have noticed is, number one, that this is a square. That means this here is 100, that's 100, that's 100, and that's 100. Because in a square, all the sides are equal. The other thing which is very, very important for us to note is that if it's a square, every one of the corners are 90 degrees. Now, that's so far so good. But when we go back to the question, it says, what is the radius of the circle to the nearest 1/100th of a millimeter? So what's the radius? Well, if I start here and I go out to the end here, that's not very helpful because there's no way I can get that distance. That's the radius, but there's no way to calculate it. But what if I were to take this and put it here? And what if I took the center part and put that over there? Now, the radius is from O to this point here, but the radius is half the diameter. So now I've got myself a triangle. Here's my right angle triangle right there, right? So I have 100, I have 100, and I have my L or my C or my A, whatever, or sorry, your hypotenuse, whatever you want to do right there. So if I can solve for this, I will get the length of the diameter of the circle. And from the diameter, you divide it by 2 to get your radius. So let's take a look at that. If you extend the line across it diagonally from corner to corner, you get your right angled triangle. That's pretty straightforward right there. So this is what I've got now. 100 millimeters, 100 millimeters, and there's my diameter. All right, I need to solve for that length. So I need you to use Pythagoras' theorem. I want you to calculate what is the hypotenuse. All right, well, take a look here. First off, we're finding the hypotenuse, so you could use h squared is equal to a squared plus b squared. Some texts use c squared equals a squared plus b squared, and some texts use l squared equals a squared plus b squared. Doesn't matter what you do as long as you recognize that this is your hypotenuse. Hypotenuse squared is always equal to the sum of the two other squares. So 100 squared, there's 2 zeros there. You double it, you have 4 zeros and 4 zeros. That gives you 20,000. Now, in order to get from h squared down to h, you have to square root it. Now, whatever you do to one side, you have to do to the other. Now, up in the question, it said to the nearest 1/100th. So we're rounding off to 2 decimal places here. So it says here that our diameter of our circle is 141.41. Now, that doesn't answer the question, does it? Because it asks us, what is the radius here? Well, in order to find the radius, we've got to go back here to this question, and we're going to have to divide the radius by 2. Okay, so I popped up my scientific calculator here, and I need 141.2 divided by 2. But remember what I told you before, that you don't use the rounded off information. So what I'm going to do first is I'm going to find the square root of 20,000 first. Right, and here's my square root right here. So if I click the square root of 20,000, I will get 141.422, whatever. Now, this is the angle I'm going to divide, this is the length that I'm going to divide by 2. And that gives me 70.71. Now, it just so happens that it works out because of the way the rounding was that it's just half of this. But that doesn't always work. So what that means is that I've got my answer here is going to be 70.71 millimeters. Oops. So there's my radius right there. So there's your answer to your question. And of course, you should have a sentence down here. All right, let's look at example 3, determining the angles in an inscribed circle. All right, now you got to be very careful with this one. First off, you have to understand that you look over here at y, it looks, very obvious that this angle from there to there and this angle from there to there are not the same. Same thing happens over here. This angle and this angle are not the same. It's harder to see with z, but it is the same root. That angle and that angle are not the same. I'll put a double arc to show that there's a difference between these. Do not make assumptions until you have the numbers that you know in front of you. All right? Moving on to the first one we're going to try and solve. We're going to try to solve x. Now, you'll notice that this goes all the way around. That's 360 degrees. So if I know this is all 360, and I know two of the parts, and there's only 1/3 left over, I can figure this out by saying that x plus 100 plus 127 has to equal 360 degrees. So I want you to solve for x right now. So pause the recording and go to the next page. There's some space there for you to write on. I want you to find out what the angle x is. All right, let's go to the next page. Here we go. It says that angle x is part of a full circle. All right, so there it is right there. So what we know is that if I take x plus 127 plus 100, I should get 360 degrees. Now, doing a little bit of algebra here, I'm going to subtract 127 from both sides and subtract 100 from both sides. The left side will all cancel out, leaving me just with x. And of course, that means that x is 133 degrees. So going back here, I can now label. I'm going to take and erase these lines here so it doesn't get too complicated, too messy. I'm going to write in the fact this is 133. We know that now. So the next question is, what else can I solve here? Does this 133 help me find z? Does it help me to find y? Well, to get y, you have to recognize that this particular angle subtends here. That's my central angle. It subtends the minor arc BC. But so does A. The A also subtends the minor arc. Now we know that central angles and inscribed angles have a relationship. The inscribed angle is actually half of the central angle. I want you to use that information and solve for the angle y. So pause the recording and do that. Okay, so let's go to the next page where there's information there. It says here that CBA and COA are related by being inscribed in central angles from the same points. So CBA is half of COA. So we have COA is 133. CBA is 133 divided by 2, which means that CBA is 66.5 degrees. So if I go out here, I know that y right here, equals 66.5. All right, so that's important. So now we got that one. We've got this one. So the other one we have to do is z. Now I helped you with the first two. I want you to find what the angle z is. So solve the equation. Solve the problem. Find the angle z for me. All right. Now, in order to get z, you have to understand something. This is a radius. This here is also a radius. That makes this triangle BOC an isosceles one. Now, if BOC is isosceles, that means the two lengths are equal, but also, more importantly, the two angles are equal. So this over here is the same. Sorry, it doesn't look like it, but this over here is Z also. So having done that, that's Z, and that's Z, and this is 133, and we know that Z has to be equal to each other. We can go and do a little bit more algebra down here. So here's angle Z. First off, it says, and I've pulled it out for you to look at, to find angle Z, examine angle AOC. And you will see that it's an isosceles triangle. If I say AOC, it should be BOC. All right, it's an isosceles triangle. Now, if you do that, that means that isosceles triangles have equal angles. So that angle there and that angle there is equal. Now, the next piece of information you need to know is that this angle here is 133 degrees. Now, 133 degrees there and two similar angles means that since this angle and this angle are equal, I can use that and the facts that they're equal to solve it because I know the internal angles of a triangle have to equal 180 degrees. So here we go. I know that the Z plus the 133 has to equal 180. So 2 Z's plus 133 equals 180. I'm going to subtract 133 from each side. Now, that means positive 133 and negative 133 are going to give me 0. And 180 take away 133 is 47. So now I'm down to 27. So 2z is equal to 47. Now, in order to get rid of the 2, I divide by what we're multiplying by. So this is 2 divided by 2. That's going to give me 1. Leave me with just 1z on the left-hand side. And 47 divided by 2 is 23.5. So that means that z is 23.5 degrees. And now it's time for your assignment. So good luck. If you have any questions, come and see me or watch the videos again. They'll help you a great deal.